Good evening to all the students and the people who have joined in this class. So, I really apologize for the delay in starting the lectures today, but that was due to some unavoidable reasons, I couldn't make it on time. So, today we'll be starting with energy materials, batteries and supercapacitors, part 1. And I'll try to wind up this lecture within the next 1 hour so that we don't lose any more time. And then we will continue with the next class. So today what I will be discussing with you is basic electrochemistry. Then we'll talk about batteries, both primary batteries as well as secondary batteries. Then I will discuss the difference between energy and power density. We'll talk a little bit about lithium-ion batteries, components and processes in lithium-ion batteries. Cathode materials for LIB I will touch upon in today's class, but then I'll continue more in the next class. So with this, first let's start. As we are talking about electrochemistry, when we are talking about this energy storage, we talk about a lot about these different storage systems, and where generally we talk about a lot about electrochemistry. So let's talk a little bit about the history of electrochemistry. So this entire story of electrochemistry, it began with Alexander Volta, and he announced his invention of the voltaic pile, which was the first modern electrical battery that was way back in 1800s. So how did Volta do it? You can see it right there on the right hand side. So what he used is the two metals which Volta used to build the pile was zinc and copper, and the alternated discs of the opposing metals with pasteboard or cloth which was dampened with brine, which is a solution of water and salt or vinegar. And then an electrochemical reaction occurred in each of these three disc unit of the pile, and it formed an electric cell and generated a current. So therefore, by changing the number of units, Volta could decrease or increase the amount of the electricity which was produced. So this was the first recorded instance of how electricity was generated using a chemical reaction. After this, William Nicholson and Anthony Carlisle, they used the voltaic pile to split water into its basic components, which is hydrogen and oxygen. And their achievement actually ushered in an entirely new branch of science, which is known as electrochemistry, which we all have studied quite a lot during our 10th, 11th, and 12th. And also sometimes people have done it in their undergraduate or postgraduate, but we will be building up on all that what you have. So this particular first 10 to 15 minutes, we will just refresh our memory on what was done, and then we will build up on that knowledge. So what are the landmark achievements in the field of electrochemistry? Very important to know when you are learning about electrochemistry. So between 1833 to 1836, it was Michael Faraday who brought about the laws of electrolysis. Then in 1836, you had John Frederick Daniel. He invented the Daniel cell. Then you had fuel cell, which was brought about by William Robert Grove in 1842. Then Gaston Plant, the lead acid battery, still a very much big workhorse, 1859. Then in 1886, you had Charles Martin Hall and Paul Herold, and they actually demonstrated the electrolytic production of aluminium. Then Nikola Tesla in 1887, he demonstrated the use of alternating current to drive induction motor. Then Arrhenius and Nernst in 1889, they stated the dependence of reaction rates on temperature and the general interpretation of the thermodynamics of electrochemical processes. In 1903, you had Cottrell who came up with the Cottrell equation, which rules the relation between electrokinetics and mass transport by diffusion. And then in 1914, you had Thomas Edison who came up with the nickel-ion battery. So these are, you can consider one of the landmark achievements till the early the first half of the 20th century. So in the first half of the 20th century, these were all the landmark achievements which we should be knowing about. So now moving further, what is electrochemistry? Just let's think about what is electrochemistry. So it is a discipline that deals with chemical reactions that involve an exchange of electric charges between two substances. So chemical change leading to electric current and vice versa. So what essentially happens over here is, it is the reactions in which the charged particles, ions or electrons, they cross the interface between two phases of matter, typically a metallic phase, which is the electrode, and a conducting solution, which is known as the electrolyte. So you have oxidant with adding in electrons, and the process is reduction, and you get a product. So electrons gain, oxidation number decreases in this process. In oxidation process, the reductant is losing electron, giving you the product. The electrons is lost in oxidation number, which increases. So this is the basic idea of electrochemistry. Now there are some concepts which you should not be forgetting, which is electroneutrality principle. So bulk matter cannot have a chemically significant imbalance of positive and negative ions. So if you are dissolving a particular metal ion in solution, it can only proceed to a measurable extent, because that is going to proceed only if you are providing some means to remove the excess negative charge that remains. So either you have an electron acceptor ions in solution, or you're drawing out electrons by metal through an external circuit. If you're able to do that, only then the dissolving process is going to happen. Otherwise, it's going to stop because it's going to follow the electronegativity principle. Then you have certain which is known as interfacial potentials. So these exist at all phase boundaries. So in case of a metal in contact with an electrolyte solution, the interfacial region consists of an electric double layer. And the potential difference between a metal and the solution is almost entirely located across the very thin double layer, leading to an extremely large potential gradient in this particular region. So how the electrode potential is going to look? If you can just look over here, what you see is that we have over here one particular solution, which I have named as A, and there is another one which is known as B. So these are two different metal electrodes. A is a more active one, whereas B is a less active one. So what you have is the development of an electric double layer, where phi 0 is the surface potential, as you can see, and phi d is the Stern potential, and phi x is the potential at a distance x from the surface. 1 is the dense part of the Helmholtz or the Stern layer, whereas 2, as you can see over here, it is the diffuse part of the medium. So what you can see is as the distance from the surface of the electrode is increasing, the concentration of the cations or the anions, they are decreasing, and it is becoming equal to the concentration in the solution. So as a result, what is happening is this electric double layer is getting formed. So while this electric double layer is getting formed, the potential difference between the electrode surface and the solution at a distance x from the electrode surface, this is known as the electrode potential. So E is equal to phi 0 minus phi x. So this is basically nothing but the concept of electrode potential. So now coming to another refreshing, what is a voltaic cell? So a device which is constructed to, harness the motion of electrons in ionic bonding, which can be used to generate electric current. This is nothing but a voltaic cell. So it will be somewhat like this. So the two electrons, they are made of different materials, both of which chemically react with the electrolyte in some form of ionic bond. So voltaic cells are also known as galvanic cells. So as you can see, you can have these half cells made of zinc electrode, and there is another half cell which is made up of copper electrode. Either you can have them in a common electrolyte, or else you can have a salt bridge between them. So what is happening is zinc loses the electron, whereas copper gains the electron, and ultimately zinc is going into the solution as zinc ion, whereas the copper is getting deposited on the copper electrode, and you see this particular figure which is shown over here, right? And then the cell potential. There is another very important concept which is cell potential. So this is a measure of how well a cell reaction can push or pull electrons through a circuit. So the electrical energy generated by the spontaneous reaction is proportional to the cell potential. Okay, so the standard cell potential is given by the difference between the cell potential, whatever you're having for the cathode, minus that of the anode. And you can also find out the change in the Gibbs free energy for this process by using this equation. Delta G0 is equal to minus NF E0, which is E0 cell. So N is the number of moles of electrons, F is the Faraday's constant, and E0 cell is the standard electrode potential. Okay. So then what we need to discuss is what is a standard hydrogen electrode, because whenever you're talking about a cell potential, it basically talks about a reference electrode, right? All these cell potentials are given in terms of some reference. So the most commonly used one is standard hydrogen electrode. You must have read through different kinds of electrodes, this reference electrode in various analytical chemistry classes, but here we don't have the time for this. So I'll just give you an idea about the standard hydrogen electrode. So what is the standard hydrogen electrode? This is a reference electrode, and all other electrode potentials, they are reference to it. So when hydrogen gas is absorbed at 1 atmosphere pressure over a platinum electrode, which is dipped at 25 degrees centigrade in 1 molar HCl, it is a regular electrode of hydrogen, and its potential is E0, which is nothing but 0 volt. So now if we have these different reactions where you can see all these reduction reactions are happening, and you have this particular potential which has been given with reference to the standard hydrogen electrode. And I have to note that more negative the reduction potential is, the more readily it acts as a reducing agent. So it itself, it is getting oxidized. So this you have to remember whenever you are having two different metals dipped into solution of the electrolyte, which is going to get oxidized and which is going to get reduced. It depends totally on this particular list, whatever see over here, this particular the list in which it shows that what is going to be the electrode potential with reference to the hydrogen electrode. Now, another very important concept is that of Nernst equation, and this is nothing but relationship between the Gibbs free energy, which we discussed, that is delta G0, with the equilibrium constant K. So delta G0 is minus RT ln K, and delta G for a reaction, it basically depends on the concentration, because Delta G is nothing but delta G is 0 plus RT ln Q, where Q is the reaction quotient. So you have the concentration of the product by the concentration of the reactant. And if you are equating this delta G with your cell potential or your standard cell potential, then you will get this particular equation, which is the Nernst equation, where E cell is nothing but E naught cell minus RT by NF ln Q, where RT and NF has already been discussed in the previous series. Now, we talked about voltaic cells or galvanic cells. Now, we have another kind of cell which is known as electrolytic cells. So, voltaic or the galvanic cells, whatever we talk about, those are all spontaneous. So, you put in the electrode materials, the reaction is very spontaneous. But when we talk about electrolytic cells, this reaction is non-spontaneous. So, the electrolysis reaction, in this particular case, it requires electrical energy to induce the reaction. So, what is the example? Is you have molten NaCl and you are electrolyzing it and you are forming liquid sodium and chlorine gas. So the concept of reversing the direction of the spontaneous reaction in a galvanic cell through the input of electricity is at the heart of the idea of this electrolytic cells. So, but you have to remember one thing, that though the direction of electron flow in electrolytic cells may be reversed from the direction of the spontaneous electron flow in galvanic cells, the definition of cathode and anode, it remains the same. So reduction is always taking place at the cathode and oxidation occurs at the anode. So your flow of this thing is different, how it is forming, but the direction of the flow, the cathode and the anode where it is happening, we have to remember reduction is always taking place at the cathode and oxidation is occurring at the anode. So what is the comparison when we do with the galvanic and electrolytic cell? The difference what it occurs is in the cell potential. So if you have a galvanic cell, you see the E0 cell over here is plus 0.78 volt. Whereas when you have an electrolytic cell, this E0 cell is minus 0.78 volt. So automatically you know that electrolytic cell, the delta G value is positive. So the reaction is not spontaneous. So non-spontaneous, but to make this particular reaction happen, you have to give it some kind of a force. And that force is when you're applying electricity or using a battery, you're providing it that amount of impetus so that the reaction happens. So copper is spontaneously plated onto the copper cathode in the galvanic cell, whereas it requires a voltage which is greater than 0.78 volt from the battery to plate ion on its cathode in the electrolytic cell. Okay. So now another very important concept which I spoke about, the first one, Faraday's law between 1833 to 1836, all these laws came in. So what was the law? The amount of substance consumed or produced at one of the electrodes in an electrolytic cell, this is directly proportional to the amount of electricity that passes through the cell. So 1 coulomb of charge is transferred when 1 ampere current flows for 1 second. So you have this particular equation, W is equal to MIT by NF. W is nothing but the mass of substance. M is molecular weight of the substance. I is the current passed in amperes. T is the time for which the current is passed. N is the number of electrons transferred. And F is Faraday constant, which is nothing but 96475 coulombs per equivalent. So the amount of chemical change is proportional to the amount of current which is being passed. Now, when you look into electrochemical cells, the number of variables is really large. So let's look into the different variables which are there. So if you have an external, now this is the kind of a layout which you have for an electrochemical cell. So you have your power supply, you have your electrodes, you have your electrolyte solution. So what are the different variables which are there? So there are some variables which are external variables and there are some variables which are internal variables. In external variables, you are having temperature, pressure, time. Then you also have these electrical variables, which is your potential, current, and quantity of electricity, which is given as Q. And the internal variables, you have the electrode material. So you have the type of material you're using, the surface area of the electrodes, you have the geometry of the electrodes, the condition of the surface of the electrodes. So all these are nothing but electrode variables. Then you have the solution variables, which is nothing but the variables in the electrolyte. So you have bulk concentration of electroactive species in the electrolyte, you have concentration of other species like your pH and all, solvent. So all these are solution variables. And then of course you have the mass transfer variables. So more, whether it's a diffusion kind of thing which is happening to transfer, whether it's a convection, surface concentration, if there is any absorption happening. So all these are the different variables in the electrochemical cell which you need to actually control and find out the right combination which is going to give you or which is going to result in the best electrochemical performance of your electrochemical cell. So you see the different processes which are taking place. Obviously, you have There's electron transfer. Then you have absorption, desorption. You have various chemical reactions. You have the mass transfer which is happening. So these are all the different processes which are happening in the electrochemical cell, and each of them are dependent on these various factors. So now one concept is there of overpotential. I say that okay, this is the kind of potential which you need to apply for this reaction to happen. But most of the time you will find that it needs a little extra push is needed. So this extra potential which must be applied to an electrode to initiate the electrode reaction. This is known as the overpotential in an electrochemical cell. So the difference between an equilibrium potential E and the applied potential EJ required to initiate the electrode reaction, this is known as the overpotential, as is given in this particular equation. So there are different contributions from different quarters which are coming in into determining the cell overpotential. So what are those different contributions? One is ohmic drop, the other is activation overpotential, the other is a diffusion overpotential. So let's see what is ohmic drop. So you have to understand this electrolyte solution, whatever is there in the cell, it always has a finite conductivity. So it always occurs between the working electrode and the reference electrode. So this contribution to polarization, this is equal to IR, okay, where I is the current density and R is the resistance. So this is the ohmic drop which happens, and to overcome this, you need to apply a little more potential than what is actually needed. Then there is activation overpotential. So this is because when the electrode reaction is happening at one or both electrodes, you will find some kinetic inhibition of one of the steps involved in the electrode reaction, like dissolution of the reactive ion or chemisorption of the reaction product, etc. So this what happens is basically over here, this is caused by slow electrode reactions. You have a slow electrode reaction, so how you can actually jumpstart it to start the proper reaction. So this reaction at the electrodes, it requires an activation energy in order to proceed. And this particular thing gives rise to this activation potential. So this is to overcome the reaction of the slow electrodes. And then there is something known as the diffusion overpotential. This is regarding the mass transfer. So diffusion overpotential at one or both electrodes is due to the presence of concentration gradients which are present in the vicinity of the electrode surface. So when you have an electrochemical reaction, the concentration at the electrode surface no longer have the equilibrium values. So now if there is the very fast migration through the electric double layer, it's a very rapid migration, then diffusion from the bulk of the solution towards the electrode, this is not going to be able to replenish the ions at the double layer quickly enough. And so what you are going to have is a concentration gradient. Now to overcome this, you have to give a little more voltage. That particular voltage, whatever you apply, contributes to the overpotential. So these are the three main factors which contribute to the presence of overpotential in all these electrochemical cells. So now with this much of the background, now let's come to the main thing, which is batteries. As I said that today I will be discussing batteries and supercapacitors. So it's a part one. So today I will be discussing mostly batteries. So battery, as we all know, is a device which converts your chemical energy directly to electrical energy. So battery consists of one or more voltage cells. So each voltage cell, it consists of two half cells which are connected in series by a conducting electrolyte. So now there are tri cells and batteries, and these are generally primary type of batteries which cannot be recharged. So how do you determine the voltage output as well as current rating of a battery? This is determined by the elements which are used as the electrodes, the size of the electrodes, and the type of the electrolyte you are using. So depending on type, cells typically have a nominal voltage potential which is anywhere between 1.2 volt to 3 volt. So now whether a battery may be recharged or not depends on the cells used to make up the battery. So a primary cell, please remember, it cannot be recharged because the internal chemical reaction cannot be restored. So you have a reaction which is basically, it's going to a completion. You cannot reverse that reaction. A secondary cell or a storage cell can be recharged because its chemical reaction is reversible. Remember, there are another type of distinction between batteries like dry cells. So dry cells, they have a moist electrolyte, so it cannot be spilled. Whereas sealed rechargeable cells, these are secondary cells that contain a sealed electrolyte, which cannot be refilled. So most of these are kind of reactions which are, these are primary cells which cannot be recharged. So now what are the common types of primary cells which you have? One is the carbon zinc dry cell. You can have an alkaline cell. You can have zinc chloride cells, you can have mercury cells, and you can also have silver oxide. So these are different types of the primary cells which you have. If you look into the cross-sectional image of this dry cell battery which I have given, so you have a carbon which is the positive electrode, then you have at the outer coating, which is zinc, which is the negative electrode. In between, what you have is a separator, which is separating this your cathode and anode. And then you have an electrolyte paste, and also you have a carbon manganese dioxide mixture. So this is what is basically inside a dry cell battery. So now alkaline cells, they have different types. You can use an alkaline cell which is A type or a C type or a D type alkaline cell. So they have the same 1.5 volt output as carbon zinc cells, but they are more longer lasting. So what it has a zinc anode and a manganese dioxide cathode in an alkaline electrolyte, which is mostly potassium hydroxide. And this works with high efficiency even with continuous use due to low internal resistance. Whereas you remember the dry cell with the previous cell which we talked about, it is better when we are having intermittent use. This one you can use more continuously. Now over here, if you look into the this picture which I have given over there, this basically shows you the different kinds of the batteries which we are having, the alkaline cells which we are having. So depending on their size, we have, their size and their look, we have these different names for them. You can have AA, you can have AAA, you can type C, type D. You can have A223, which is a 12 volt one. Then you have PP3, which is a 9 volt one. You have CR2032, these are the 3 volt small batteries, cylindrical batteries, and you have LR44 batteries. So these are the different names of these different batteries which are available in the market. So coming to the zinc fluoride cell, this is also known as a heavy duty type battery. Okay? It is a modified zinc carbon cell. Why it is modified? Because it has little chance of liquid leakage. This particular cell, it consumes water along with the chemically active material. So what happens is the cell becomes dry at the end of its useful life. So these are heavy duty type of battery, the zinc fluoride cells. Then you have mercury cells also. Previously, definitely there used to be a lot of mercury cell. Now it's more or less obsolete because, of course, the hazards which are associated with the proper disposal of mercury. So in this particular cell, what you have is a zinc anode. You have a mercury compound cathode and potassium or sodium hydroxide, which is used as the electrolyte. So this mercury compound cathode is something which we try to avoid because of the health hazards of mercury, and that is why this particular mercury cells are right now quite obsolete. Then another cell which you have is a silver oxide cell, still available in the market very much. So this cell consists of zinc anode, it has a silver oxide cathode and potassium or sodium hydroxide electrolyte. So it is typically available as 1.5 volts, miniature button form, the silver oxide cells. Applications, they are mostly found in the hearing aids and cameras and watches. So all these different cells, the smaller ones, these miniature button form cells we use are mostly the silver oxide cells. Now coming to one of the powerhouse, this is a lead acid wedge cell. So this cell is a widely applied type of secondary cell. What is secondary cell? That means this particular reaction, the cell reaction in this case is reversible. So you can charge it and you can discharge it and you can use it again and again. It is not a use and throw type. You can charge and discharge this particular cell. Okay. So this cell is widely applied type of secondary cell. It is used extensively in vehicles and other applications which require high value of load current. So the positive electrode for this particular lead acid wedge cell is made of lead peroxide, and the negative electrode is spongy L20. Electrolyte is sulfuric acid. Voltage is around 2.1 volt per lead acid cell per cell. And these cells are typically used in series combination of 3, so where the voltage is added up and you get 6 volts. Or you are having combination of 6 of them together to give you a 12 volt value. So this is how generally lead acid wedge cell is used. So if you look into the reaction during discharge, what is happening? Lead and lead peroxide along with the sulfuric acid, it is giving rise to lead sulfate and water. So as the cell gets discharged, you get more and more water getting generated. Whereas when you charge the cell, this lead sulfate and water, they again react back with lead peroxide and sulfuric acid. So the current regime for this is how much discharge current they can supply for a specified amount of time. And the unit is generally ampere hours. So what you have over here is that the specific gravity of the lead acid wedge cell, this is actually very important because specific gravity, it actually tells you the state of discharge or how much charge the battery has left when you are measuring the specific gravity of the electrolyte cell. So whenever you want to know that how much charge is left in a lead acid wedge cell, what you have to do is you have to check the specific gravity of the electrolyte because water is generated when you are discharging this cell. The specific gravity is changed. So, so in this particular equation, you can see this, in particular this figure, you can see that when you are charging it, you are actually getting this particular reaction. So as the cell discharges, more water is formed, lowering the specific gravity of the electrolyte. And when you are charging it, then again this water is used up and you are forming lead peroxide and sulfuric acid. The other cell which we will talk about is the nickel cadmium cell. This type of cell, it actually delivers very high power and it can be recharged many times and can be also stored for a very long period of time. So that is why the applications are mostly nickel cadmiums are found in portable power tools, alarm systems, portable radio TV equipments. So the reaction is the nickel hydroxide is reacting with cadmium during discharge. It is giving you nickel hydroxide and cadmium hydroxide. And when it is charging, it is again giving you nickel hydroxide and cadmium. And the electrolyte in this case is potassium hydroxide, but it doesn't actually take part in the reaction. Its job is to act as a conductor for the transfer of the hydroxyl bonds. And please remember the specific gravity does not change with the state of charge for this particular nickel cadmium cell. Now the nickel cadmium cell, the biggest problem with nickel cadmium is the cadmium, because cadmium is actually, we know, very toxic. So we want to avoid the cadmium part. And that is why this new technology was there, which is nickel magnesium metal hydride cell. So this is used in applications which demand very long-running battery performances. For example, high-end portable electrical or electronic products like power tools. It offers 40% more capacity over a comparably sized nickel cadmium cell. So the only thing which is different from the nickel cadmium cell is obviously the cadmium negative electrode. So instead of that, you have a metal hydride electrode. So these are generally more expensive than the nickel cadmium cells. They self-discharge more rapidly. It cannot be cycled as frequently as nickel cadmium cells, but the biggest point is they are much more safer and much more environment friendly compared to the nickel cadmium cells. So now we have these cells having their own voltage coming in, like somebody is in 1.5, somebody in 2.1. So what we have to do is we have to connect these cells in a series or parallel. And when we connect these cells in a series form or in a parallel form or in a combination of both, then that entire unit is known as the battery. The individual things are known as the cell, and when you're combining all of them in a series or a parallel or in a combination of series and parallelly connected cells, then this is known as battery. So an applied voltage higher than the voltage of one cell can be obtained by connecting cells in series. The total voltage available across the battery of cells is equal to the sum of individual values for each cell. Parallel cells, they will have the same voltage as one cell, but they will have more current capacity. So to provide a higher output voltage and more current capacity, cells can be connected in series and parallel combination. And these combination of cells, as I said, is called a battery. So let's look into it. You have three 1.5 volt cells which are connected in series. So ultimately the total voltage you find is 4.5 volts, and these are the three different ways you can represent. The last one is basically when the battery is connected to a lead resistance which is given as L. Similarly, you can have a parallel combination of three 1.5 volt cells. In this case, the voltage which you get across the terminals is again 1.5 volts. But definitely, this parallel connection is equivalent to increasing the size of the input of the electrolyte. This actually increases the current capacity. So what the current you will get is much more than you get from a single cell. But the voltage is going to be the same. Then you have series and parallel connected cells, as you can see over here. And when you are doing this, you can actually see how you can schematically, you can represent when you have 2-3 volt cells which are connected parallelly, the output voltage which is coming is 3 volt. And when you are having a voltage of 3 volt and the current is around 100 the current which you get is 100 milliampere, when you are having a resistance of 30 ohms. Whereas if you keep on changing the resistance, the amount of current which is generated by this particular circuit is going to differ, and this is going to be given by Ohm's law, which is I is equal to P by R, or B is equal to R as we see. So the actual amount of current produced when the battery is connected to a load resistance is given by the Ohm's law. So now this is basically the idea. Okay, idea of all the different things which are there in electrochemistry, which we will now build up. All these things you have heard many times in different levels of whenever you are studying, sometimes in your high school, sometimes in your undergrad studies, sometimes in your postgrad studies, from all people from the different backgrounds, joining this class. So now we are going to build on whatever we have done. So now let's look into the energy utilization thing. Why it is so important to have all these kind of different batteries and storage systems? So efficient harvest, storage and management are three essential segments to energy consumption in modern society, and I'm sure all of you will agree with it. So what you are having, you have now, instead of fossil fuel, we are depending more and more on renewable energy. We want to harness renewable energy. Renewable energy, as you all know, is intermittent in supply. You will not get it like continuously. So sometimes when the sun is shining very high or we have lots of wind, you are generating a lot of energy. But that entire part probably is not needed in the grid at that particular moment. But then there are times when it is, when it is night time, when you are not having the sunshine, or else it is not a windy day. So the power is not getting generated. But then you need power in the grid. So to actually put in a continuous power supply, the thing which is most essential is storage. And this is where basically your batteries nowadays finding a lot of application. Then another very big application of batteries nowadays is like for fossil fuels you're using for cars. We now also want to have these battery-driven cars, and you can see that it's come very much into the market. So EVs, why the benefits of going electric, we all know, improve air quality. You have less amount of greenhouse gas emissions. Then you have superior technology. They have superior technology compared to these internal combustion engines. Reduced operational maintenance cost, which is getting further and further decreased in the long run. So these are all the benefits of going electric. So right now, you see, from it started around 1890, but now in 2006 onwards, Tesla has begun producing all electric sports car. So lead acid batteries were anyway they were being used, in these different vehicles and all. But now, right now, what we are using in all these electric batteries, electric vehicles, is lithium-ion batteries, which is the fastest growing battery system. Lithium ion is used where high energy density and lightweight are of prime importance. That is from 100 to 265 watt-hour per kg, no maintenance requirement. Lithium-based batteries, they continue to improve. So you can see over here these different battery technologies which has been given, specific energy versus specific power. And you can see exactly where lithium ion is sitting. It's having a good combination of specific energy as well as good specific power. So this battery, when we talk about battery-driven cars, this is where lithium-ion battery technology is coming into the picture. So predictions of EV cost parity with this internal combustion engines. If you see over here in this pink mark thing over here, you can see in 2024 EV cost parity crossover with IC cars and capital cost alone. And this has already happened. And you can see in Mumbai roads right now, there are so many electric vehicles which are running. So this has already happened. And with this, you can imagine the strain which has come into the battery market, because lithium ion is not that well, lithium metal is not that well available in trust. So it is putting a lot of pressure on our resources. So this is definitely one technology which is increasing by leaps and bounds. So you need it for storage of your renewable energy. You need it for your electric vehicles. So lithium-ion battery technology is definitely one of the prime technologies which you need to have knowledge about when you're talking about energy storage at this present time. So the importance of this work, the work started very, very long back, right? Way back in 1970s. But the importance or the acknowledgement for this work came in through the Nobel Prize in 2019, which was given to three famous scientists, John B. Goodenough, M. Stanley Whittingham, and Akira Yoshino. And they were given the Nobel Prize, they shared the Nobel Prize for development of lithium-ion batteries. And according to the Nobel Foundation, they said that this lightweight, rechargeable, and powerful battery is now used in everything from mobile phones to laptops and electric vehicles. And it can also store significant amounts of energy from solar and wind power, making possible a fossil fuel-free society. So now, if you see by 2030, the lithium-ion battery supply chain is projected to grow to over $400 billion as more gigafactories emerge all over the world. So you can imagine the kind of explosion of application lithium-ion batteries are having, and it doesn't show any sign of slowing down. So it's very important to know about this particular technique or this technology. So what happens in a lithium-ion battery? This lithium ion is shuttled between a host, which is the anode, and that is at a higher chemical potential, and the different host, the cathode, that is at a lower chemical potential. So in the lithium battery, as opposed to lithium ion, the anode is lithium ion. So remember, there is a lithium ion battery and there is a lithium battery. When you're talking about lithium battery, the anode is lithium, whereas in a lithium ion battery, the anode is nothing but graphite. The commercial lithium ion batteries, they have graphite as the anode. So what was the contribution of each of these scientists? So first were the three who got the Nobel Prize. So what was the contribution of Stan Whittingham? So he wrote this, he came out with this very important paper in the Journal of Electrochemical Society way back in 1976. It was the role of ternary phases in cathode reactions. So what he showed is that lithium metal can be shuttled between a cathode and anode, and in this case, what he used was a titanium sulfide cathode, and lithium metal was used as the anode. So this first attempt worked because it was based on metallic lithium anode, which was found to be chemically reacting with the electrolyte, leading to. But the problem was that this particular thing, it was reacting with the electrolyte, and it was leading to instability and growth of lithium whiskers. So if there is whiskers, that is the dendrite. What is happening? It is perforating through the separator. It is going and touching your cathode, and the moment it is doing that, then basically there is a short circuit and the battery was exploding. So that was the problem. But he showed that okay, lithium is shuttling between the cathode and anode, and with this, there is a movement of the electrons on the external circuit, whereas there is a movement of the lithium ion internally. So then, what was the contribution of John Goodenough? So what he brought out this particular paper, this paper, he said lithium cobalt oxide, which is a new cathode material for batteries of high energy density. So whereas Whittingham, he worked on sulfide, that is titanium sulfide as the cathode, John Goodenough found out this amazing cathode material, which is lithium cobalt oxide. And this particular material is still being used in the commercial lithium-ion batteries because it's one of the best known cathode materials so far. So lithium cobalt oxide is being used as the cathode. Obviously, now you want to go cobalt free and you are doing a lot of development on the cathode side that we will discuss later. But as of now, also in the commercial scale, you will find all the lithium-ion batteries still using the lithium cobalt oxide as the cathode. So this was the cathode which was used, and they used lithium metal as anode. So this was his contribution. Whereas the contribution of Akira was that he changed the anode. The moment he changed the anode, the moment he replaced lithium anode with that of highly graphitic carbon, showing that graphite has the capability of intercalating lithium ions in between its layers, that was actually the master stroke, because that stopped the problem of the lithium whiskers or lithium dendrite formation, and it gave safety to the lithium ion batteries. And this is basically the commercial battery which came in with lithium cobalt oxide as the cathode, graphite as the anode, and the electrolyte using lithium salt. And we see that lithium carbonate as well as dimethyl carbonate solvents. So what happened is with this in 1991, the lithium-ion battery was commercialized by Sony and Asahi Kasei Corporation, with Samsung SDI beginning the manufacturing of the lithium-ion batteries at their Cheonan, Korea plant in 2000. So this was the beginning of the entire journey of the lithium-ion batteries. So now if you look into the schematic representation of a lithium-ion battery cell, this is how you have. The cathode is lithium cobalt oxide, and the anode is your graphite. And basically, when you are actually charging it, you are moving the lithiums from the lithium cobalt oxide above, it is going and it is intercalating in between the graphite layers. Whereas when you are discharging, it is moving back from this graphite, it is moving back and it is coming into the lithium cobalt oxide, the cathode form. So this is how the charging and discharging is happening in a lithium-ion battery. So now we have to know some common terms related to batteries because we will be using it quite often. What is power capacity, which is energy that gets stored in a battery? It is measured in watt-hour. Power capability, maximum amount of current that the battery is capable of delivering. This is also termed as C rating. Then you have something which is known as a nominal voltage. Since the voltage of the battery stays constant and is not variable, it is a nominal voltage. That's a fixed voltage. Then you have a charging currents. Maximum amount of current that can be applied to the battery for charging. The self-explanatory is charging current. Charging voltage is maximum amount of voltage that must be applied to the battery to charge it efficiently. So these are some common terms which we all use. Then there is something known as discharging current. So what is this? It's the maximum amount of current that can be drawn out of the battery and delivered to you. If the current draw exceeds the stated discharging current, the battery drains up fast, causing it to heat up and it might also explode. So it is very important to have a kind of a check on the discharging current. Then you have shelf life of batteries. In many batteries, you'll find that it keeps on self-discharging. So if you keep a battery idle or sealed for a very long span in the shops, then the shelf life is the time for which the battery can stay powered up and usable. It is mainly present for non-rechargeable batteries as they are for single usage only. The rechargeable batteries with lower shelf life are still rechargeable after this. So if you remember, the shelf life of a battery, this is more applicable in case of primary cells compared to the secondary ones. For the rechargeable ones, even if there is some self-discharge, you can again, charge it up and you can use it. Then you have something which is known as a cutoff voltage. So this is the voltage for which the battery might get considered as completely discharged. So if we try to discharge the battery after that voltage, it will get damaged. Then you have something which is a cycle life of battery. We say the battery, the cycle life of the battery has gone. This means that when it discharges to 80% of its original capacity. So when you charge and discharge a battery, if it is not able to revive to beyond 80% of its proper original capacity, that is the time you say that the cycle life of the battery is over. Okay, so it discharges to 80% of its original capacity. So now we have something which is also known as the Ragon plot. So this is the plot which is used to compare the energy density of various energy storing devices. So what you have over here on the x-axis, what you have is the power density, which is given in watt per kg, and the y-axis, what you have is the energy density, which is given in watt hour per kg. And both this axis, please remember, a logarithm. So you can compare the performance of very different devices. So conceptually, this vertical axis is describing how much energy is available per unit mass, whereas the horizontal axis is showing you how quickly that energy can be delivered, or which is the power per unit mass. So a point in the Ragon plot, it represents a particular energy device for a particular technology. So you can see over here, you have right at the top, in the left topmost corner, you have something which is the fuel cell. There is the fuel cells, we have the highest watt energy density. Whereas if you look into lithium-ion battery, it has high energy density but comparatively low power density. Whereas the power density is mostly in case of the capacitor. So in Ragon plot, you are actually able to make out that which device, wherever it falls in the Ragon plot, it tells you that whether it is giving high energy density or it is giving high power density. And ideally, what I want is something which should be right there at the right-hand corner, topmost right-hand corner, which should be very high power density and very high energy density. As of now, we are not there. But lithium-ion battery is something which is giving you a high energy density, a comparatively low power density, whereas capacitors give you very high power density and low energy density. So what is the voltage of a battery? So what you have over here, the cell voltage is determined by the compatibility of the whole system. So you have anode, cathode, electrolyte all together. So cell voltage is determined by that. And how do we give this? So the difference, this is basically the difference in chemical potential. The anode is made up of a material, the cathode is made up of a material. Like over here you have lithium cobalt oxide and you have graphite in case of lithium ion battery. So the chemical potential of the cathode and the chemical potential of the anode, the difference between it is nothing but which is known as the open circuit voltage of the battery. So now this open circuit voltage is limited by what? It is limited by the electrochemical window of the electrolyte. So the electrolyte also has this HOMO and LUMO level. You have this different salts over there with this, different kinds of solvent which are there. So now this open circuit voltage, whatever you see in a battery, this is limited by the electrochemical window of the electrolyte. So the anode and cathode, when you select it, it must be such that the chemical potential of the anode lies below the lowest unoccupied molecular orbital of the electrolyte, whereas the chemical potential of the cathode should be located above the highest occupied molecular orbital of the electrolyte. Okay. So this is where basically you are limited. So this VOC or the open circuit voltage is limited by the electrochemical stability window of your electrolyte. So whenever you are choosing this particular anode and the cathode material, you have to, that's why we are saying that in totality we have to see how the voltage is, because all these three things have to move. Because if it doesn't, then there is going to be a decomposition reaction. And when this happens, the electrolyte will be reduced on the anode or oxidized on the cathode, and they will form a passivating solid electrolyte interface, which is known as a SCI film. This solid electrolyte interface, in short, it is known as an SCI film, and this generally forms on the anode. So, but this SCI film formation is not all bad. SCI film formation is good. Why? Because it permits the diffusion of lithium ions through the film under a uniform electric field. It reduces the overpotential and concentration polarization. So it reduces the overpotential what you need. So this is a good part of SCI formation.
It also prevents aggregation of the electrochemically active particles, and it maintains a uniform chemical composition at the electrodes. So in SEI, it can effectively prevent the exfoliation of graphite during the insertion and extraction of the lithium ions. However, the problem with SEI is that it increases the internal resistance of the battery. Also, when you are forming the SEI, some amount of the lithium, which has decomposed, suppose from the lithium cobalt oxide, that stays in the SEI film. It is not able to come back from the anode to the cathode. So that amount of lithium is lost. And the moment you are losing that much amount of lithium, what happens is you are losing capacity as well as you are losing power. So that is why SEI film formation, whenever it happens, what happens is you never get a Coulombic efficiency, or the initial Coulombic efficiency is never 100%, because some amount of lithium is always lost in the formation of this SEI layer. What is the theoretical capacity of the electrode materials? So this corresponds to the number of reactive electrons and the molar weight of the designed electrode. So when we say theoretical capacity of an electrode, like we say that the theoretical capacity of this particular anode is this much. How will I say it? So we have this N, which is the number of reactive electrons which are moving, in that particular electrochemical reaction. F is the Faraday constant, and M is nothing but the molar weight of the material. So the number of electrons is correlated with the number of lithium ions which is accommodated in the host lattice. This host lattice is nothing but your anode, because cathode is anyway lithium rich, it's having the lithium. Then, so the smaller molecular weight and accommodation of more electrons per formula unit, obviously you can see as per the equation, because Ct is directly proportional to N and is inversely proportional to the molecular weight. So, if you want to increase basically the capacity, then you have to either increase N or you have to decrease N. The energy density, so this is the capacity, and energy density is what? This capacity which is multiplied by the working voltage. So if you want to improve the energy density of your thing, you have to work on what? You have to work on the specific capacity, which is basically dependent on the material which you are using to form the electrode. Whereas there is another way which you can do which is you can improve the working voltage, and for that you can also work on the electrolyte part, because if your electrolyte is having a more stability window, then you can actually have materials with more amount of chemical potential in the anode and less amount in the cathode, and then you can adjust it. So two factors on which your energy density depends: specific capacity and the working voltage. This you have to remember. So what are the elements available for design of new electrode materials? So as I said, lighter elements are favored because this is going to give you higher capacity. Then you also have to see that natural abundance is there, because if something is not naturally abundant, then it will bring up the cost and you cannot use it in a bulk level. Then there is lack of competition with other industrial applications that should be there. Eco-friendly nature for processing, usage, and recycling should have a low cost. So technologically, the electrode materials must offer a large reversible storage capacity at a desired electrochemical potential. So metal lithium anode, see if you are having metallic lithium as anode, then the theoretical capacity, if you calculate using the equation I gave you, it is 3,850 milliamperes hour per gram. In case of silicon, it will reach a value of 4,200 milliampere hour per gram. So, and this is how will you determine that? What is the type of combination it is having with the lithium? In case of lithium metal as anode, whenever you are having, in that case, it is 3850 because of the kind of alloying power it is having, whereas in silicon, it is 4200 because the alloying compound which is forming is Li22Si4. So 22 lithium ions and atoms are getting encapsulated within 4 silicon atoms. So that is why you are getting such a high value of this capacity of this particular material. So what are the different factors on which this electrochemical potential of electrode depends? One is electronegativity. What is electronegativity? We already describes the tendency of an atom or a functional group to attract electrons towards itself. So if you have very large difference in electronegativity, it has a more ionic bond. And if it is a small difference, then you will be having a covalent bond. So always remember that materials with more ionic bonds, typically they form dense structures, whereas those with covalent will generally have a poorly packed structure. So this structure density, it influences the crystal and the phase stability of the materials. It also affects the specific site energy of lithium ions. And all this is correlated with the electrochemical potential of the material. So that is why electronegativity of the material, whatever you are using in the electrode, will play a very important role in determining the electrochemical potential, whatever you get for your particular cell. Then you also have dependence on the number of electrons in the d orbital of the transition membrane. Like for you are using cobalt, right? So it has a number of d electrons. Like cobalt, if it is in a 4+ state, you have d5. If cobalt is in a 3+ state, you have 6 d electrons. So generally, what is seen is that the potential it increases with the increasing number of electrons in the d orbitals. Okay. So the more energy released when electrons are inserted into orbitals, or the more energy which is consumed when electrons are promoted from orbitals, the higher is going to be the electrochemical potential of the electromaterials. Then something which you have again is basically, so suppose we are comparing the potential of the various phosphates which we are having of these different metal ions. Let us compare bismuth and molybdenum. Bismuth is belonging to periodic 6. And group 5 of the periodic table. It has a very large atomic number and a large electronegativity. So it has a very high electrochemical potential. As you can see over here, all the bismuth compounds are having a potential versus lithium ion almost to the level of 5. Whereas if you look into molybdenum, these are all phosphate compounds. So that, the anion is common. So in this case, what you have is for the molybdenum phosphate, the potential is somewhere between 3 to 3.5. So this is because why? Because molybdenum is having a lower electronegativity and a relatively small atomic number. So these are the factors which affect the electrochemical potential, and this is how you can actually think about which material to choose for your electrodes. Similarly, if you look into over here the anion part, I talked about the metal ion part. Now look into the anion part. You can have silicates, you can have phosphate, you can have molybdate, you can have sulfate. So if you look into lithium ion silicate and lithium ion phosphate, that green block if you see. So between the silicate and the phosphate, when you change this anion, what you find is the potential is increasing. Why? Because it increases with the electronegativity of the polyanionic group. The phosphate polyanionic group is having more electronegativity compared to the silicate. So it has a more potential. Okay. Similarly, if you look into phosphate versus molybdate versus sulfate, which is basically the blue block which I have shown over here, you will again find that in phosphate you are having 2.8 volt. Molybdate it is 3 volts, whereas it is for the sulfate it goes up to 3.6 volts. So you can see how you can actually, when you are doing research, you can look into what material is going to be more useful for you if you want to have a material or an electrochemical cell which is going to give you more amount of capacity or more energy density. So you can work around with these various electrode materials. So selecting elements is the first step, wherein the atomic weight, abundance, environmental impact, and cost are to be considered. Then what you are need to consider is the electronegativity of the elements and the counter anions, which are key parameters which determines the electrochemical potential of these various electrode materials. So today I will stop over here, and then we will continue again on Monday's class. What I would request all of you is to go through the slides, and in case you have any question, you can obviously post it to me, and I will give you an answer to all your questions. With this, I would like to end the class today. Thank you very much, and I apologize once again for the delay starting the class. Next class will start right on time at 4 p.m. Good day.